Industry skills, practical knowledge, real-world impact. This is SimpleGyan.
Could a hard maize kernel be transformed into a clear, sweet liquid used in confectionery, medicines, beverages, and bakery products? The surprising answer is yes, but the factory does not simply squeeze sugar from maize. Instead, engineers first separate the kernel into starch, protein, fiber, and oil. The purified starch is then broken down by enzymes into glucose molecules. So, how does an industrial plant turn maize into glucose? Let us follow the complete journey from the storage silo to the final syrup tank. A maize kernel is a compact biological structure. Its largest portion is the endosperm, which contains mainly starch and protein. The outer layer contains fiber, while the germ contains valuable maize oil. A typical kernel contains approximately 60 to 70% starch, 8 to 10% protein, 3 to 5% oil, fiber, moisture, and minerals. The factory's first objective is to separate these components without unnecessarily damaging the starch. This is accomplished through a process called wet milling. The process begins when maize arrives at the plant by truck or rail. Samples are tested for moisture, damaged kernels, fungal contamination, and foreign materials. Maize that passes inspection is transferred into large storage silos. Before processing, the kernels move through vibrating screens, aspirators, destiners, and magnetic separators. Screens remove oversized and undersized impurities. Air removes dust and husk. Destoners separate stones, while magnets capture metallic particles that could damage downstream machinery. Clean maize is then weighed and sent to the steeping section. Steeping is one of the most important stages of wet milling. The maize is soaked in warm water, normally around 48 to 52 degrees Celsius, for approximately 30 to 48 hours. A small, carefully controlled quantity of sulfur dioxide is commonly added. The steeping liquid penetrates the kernels and softens their internal structure. It helps loosen the bonds between starch and protein and restricts unwanted microbial growth. During this stage, some soluble proteins, sugars, and minerals enter the water. The resulting liquid, called steep water, is not necessarily discarded. It can be concentrated and combined with fiber to produce nutrient-rich animal feed ingredients. After steeping, the maize kernels are soft, swollen, and ready for mechanical separation. The softened kernels first pass through coarse mills. The purpose is to open each kernel without crushing the oil-rich germ into very small particles. Water is added to create a pumpable slurry. The slurry then enters hydrocyclones, where separation occurs according to density. The lighter germ moves toward one outlet, while the heavier starch, protein, and fiber leave through another. The separated germ is washed, dried, and sent for oil extraction. It eventually becomes maize oil, while the remaining germ meal may be used in animal feed. This makes maize processing a multi-product operation, not simply a glucose factory. After germ removal, the remaining material is finely ground to release the starch and protein trapped inside the endosperm. The slurry passes across specially designed screens. Large, fibrous particles remain on the screen, while the much smaller starch and protein particles pass through with the water. The fiber is repeatedly washed to recover any remaining starch. It is then dewatered and dried, often becoming an ingredient in maize gluten feed. The liquid passing through the screens is known as mill starch, although it still contains both starch and gluten protein. These two components must now be separated. Starch and gluten differ slightly in density. Industrial centrifuges exploit this difference. When the mill starch enters a high-speed centrifuge, the denser starch separates from the lighter protein fraction. The gluten-rich stream is concentrated and dried. Because it contains valuable protein and natural pigments, it can be sold as maize gluten meal for specialized animal and poultry feeds. The starch stream is cleaned through multiple washing stages, often using hydrocyclone systems. At the end of this section, the plant obtains a highly purified suspension called starch milk. This purified maize starch is the raw material for glucose production. Starch itself is made from thousands of glucose units connected in long molecular chains. However, it is not yet a sweet, readily usable glucose solution. First, the starch milk is adjusted to the required concentration and pH. An enzyme called alpha-amylase is added. The mixture is heated, commonly to temperatures above 90 degrees Celsius, depending on the enzyme and plant design. Heating causes starch granules to absorb water and gelatinize. Alpha-amylase then cuts the enormous starch molecules into shorter carbohydrates called dextrins. This process is known as liquefaction. The thick starch paste becomes a less viscous liquid that can flow more easily through the processing equipment. The liquefied starch is cooled and its pH is adjusted for the next enzyme. Glucoamylase is then added to break dextrins into individual glucose molecules. In some processes, an additional debranching enzyme may be used to improve conversion. The mixture remains inside large saccharification tanks for many hours under carefully controlled conditions. Temperature, pH, enzyme dosage, and holding time determine the final sugar composition. This is the stage where maize starch truly becomes glucose. Chemically, water participates in breaking the bonds between the glucose units. This reaction is called hydrolysis. The resulting product is a dilute glucose solution, but it still needs purification and concentration. The glucose solution may contain traces of protein, color, salts, and fine suspended particles. Filters remove insoluble matter. Activated carbon absorbs unwanted color and organic impurities. The liquid may then pass through ion exchange columns where dissolved mineral ions are removed. After purification, the syrup becomes clear, clean, and suitable for food or industrial applications. Throughout the process, laboratories test parameters such as dry solids, pH, color, microbial quality, and dextrose equivalent. The dextrose equivalent, or DE value, indicates how far the starch has been converted into reducing sugars. A higher DE generally means a sweeter syrup with a greater proportion of small sugar molecules. The purified glucose solution still contains a large amount of water. It enters multi-effect or vacuum evaporators, which remove water at reduced pressure. Operating under vacuum lowers the boiling temperature and helps prevent excessive color formation or product degradation. The syrup is concentrated until it reaches the required solids content. The final liquid product is commonly known as glucose syrup or corn syrup, depending on the market and specification. If crystallization is required, the glucose solution undergoes further concentration, controlled crystallization, centrifugation, and drying. Therefore, one production line can manufacture either liquid glucose syrup or solid dextrose products. Maize-derived glucose is used far beyond ordinary sweetness. In confectionery, it helps control crystallization and gives products the required texture. In bakery items, it contributes to browning and moisture retention. It is also used in ice cream and dairy products, jams, sauces, and beverages, pharmaceutical syrups and tablets, oral glucose products, fermentation processes, adhesives, paper, and other industrial applications. Different applications require different syrup compositions, viscosities, and purity levels. It is also important not to confuse ordinary glucose syrup with high-fructose corn syrup. High-fructose syrup requires an additional enzymatic process that converts part of the glucose into fructose. A modern maize processing plant is designed to use nearly every valuable fraction of the kernel. From approximately 1 ton of clean maize, a plant may recover roughly 600 to 650 kilograms of starch on a dry basis, although the actual output depends on the maize variety, moisture content, and processing efficiency. That starch can then be converted into glucose products. At the same time, Germ provides maize oil, gluten becomes protein-rich feed, fiber becomes feed material, steep water provides soluble nutrients, water is recovered wherever possible, while heat integration and multi-effect evaporation reduce energy consumption. This integrated recovery system is what makes large-scale maize wet milling economically viable. The journey from maize to glucose is not a single chemical reaction. It is a precisely coordinated combination of agricultural science, mechanical separation, enzyme technology, filtration, and thermal engineering. The kernel is cleaned, softened, opened, and divided into its valuable components. Its starch is purified, liquefied, and hydrolyzed until long carbohydrate chains become simple glucose molecules. So, the next time you see glucose syrup in a food, medicine, or industrial product, remember, it may have started its journey as a single maize kernel in a farmer's field. If you enjoy learning how industries transform everyday raw materials into valuable products, subscribe to SimpleGyan Engineering for more engineering and manufacturing documentaries.